Oh, hey, Mark, how's the Pokedex coming? Are you still working on that?
No, I've been playing Kingdom Hearts.
Oh, tight.
It's not going well.
Oh, are you doing critical mode?
Yeah,
Word.
I'm doing it on number 3. I already beat number 2.
Nice. Holy crap. Even Sephiroth on critical mode?
Yep.
Oh, yeah, now you got it. Yeah, you have nothing to worry about in 3 then.
Even Terrath.
Oh, yeah, that's right. You might have to worry about that.
Yeah, it's really bad.
Um, Anyway, today we're gonna forego a warm-up, everybody, just because I want to be able to roll on to the section. It's an important section, so I don't want to dilly-dally. Today we'll be talking about probability. We'll get going at about 8:20 just so that everybody has the regular 5 minutes to log in. Then I'll take attendance, and then we will learn what we need to learn about basic probabilities. Though, like I said, it's a wholly incomplete lesson, right? This is just the primer. So, of course, if you have any questions, stop me and ask. It's good to ask that stuff now. Just be aware that if it's like a specific application question, like, oh, for this given scenario, how would I calculate the probability? Those are a lot harder for me to answer for y'all, only because we might not have all of the vocabulary and tools to answer all of your individual questions out there, especially if they're actual questions about applying this stuff to the real world. You'll see what I mean tomorrow morning almost instantly when we do our warm-up question. Tomorrow we're going to look at a classic question from statistics that I guarantee all of you will get wrong, with maybe 1 or 2 exceptions, but the overwhelming majority of y'all will get tomorrow's warm-up question wrong. But then after you have it explained to you, it becomes very obvious. That's definitely the way that learning statistics feels. It's super hard to try and get your feet on the ground, planted with a strong foundation to deal with stats, just because it's so different in its thinking from all of the math that you've learned up to this point. Okay, I'll go ahead and take attendance now, and then we'll get going. And it'll somehow be the last section of the school year. Oh. Are your other classes meeting today?
We stopped all our other classes.
Really?
Yeah, we don't meet anymore.
Yeah.
Is it because they're AP or?
No, we just stopped all our other classes. Because technically, I guess school ended yesterday because these next 2 days were technically final days.
Yeah, but there's an email that says that because we're not having finals to continue regular classes through what would have been final days.
Yeah, I think they just ended it because I think everyone's checked out and they're just.
Yesterday we did have a Zoom for Sophie though, but it was like a potluck.
Yeah, and then today
virtual
we're gonna.
potluck.
Mm-hmm.
Oh, word. Though, sorry to be a hater then in your schedule and make you guys get up today. This is the last lecture though, so there's that. And we are still going to meet tomorrow. Okay. So today all I'm going to talk about is our last lecture of the year. Today we'll be discussing a bit of the ins and outs and the mechanics of probability. So just so you know, what we're going to look at, what we are going to look at today has a couple requirements, a few assumptions that we're going to make, like mandatory simplifications, so that this there we go. So that this work has a chance of making sense. And just so you know that today we are going to assume that events are equally likely unless otherwise noted. We always have questions or worries about details or specifications or whatever, but all I'm saying here is take all of that stuff, throw it out the window. So if we're talking about like a deck of card problem, you don't have to worry about whether or not the deck of cards is fairly shuffled. You don't have to worry about whether or not the deck of cards is missing a card, or if one of the cards is wrinkled in the middle, and as such, it's more likely to stick to the cards around it in shuffling, causing some issue with the order. If we're talking about a deck of cards, I'm not actually talking about the physical object 52 cards. I am talking about a magical arrangement that is somehow perfect of 52 elements that have certain markings on them. But when it comes to discussing those types of problems, we remove all of the physical features and all of the complications that can arise from those physical features. That might
Mr.
sound
Robinson?
dumb. Yeah.
I'm sorry for cutting you off, but this is kind of a random question. You're gonna keep this YouTube channel, right?
What do you mean keep it?
Like, let's say next year or the year after, if we want to come back to these videos, is it gonna be here?
Oh, that's a good question. I doubt it, and that's only because the school has a like G Suite account for us to run the school's emails through Gmail, and that YouTube account is made with that email. So I'm going to assume that when that email account goes away, so do all of the accounts associated with it.
Oh,
Yeah, I think that account goes away.
alright.
I mean, but hey, if there's any particular things in there that you want to maintain or whatever, there's all sorts of ways that you can download videos from YouTube, like if you figure out how to do that, in case there's a few things that you want to store locally.
Yeah.
Hey, anyway, but here's why I bring this up about saying like the deck of cards has no physicality that we're interested in. That's because people always try and wheedle away at statistical type arguments by making statements like that, statements about the real situation on the ground. So that happens a bunch, especially with these like COVID-19 projections. Like the scientists are like, hey, we're headed towards 350,000 dead and da-da-da-da-da. Well, people are like, well, what if we were to change this? Or what if we were to change that? Or what if the disease actually behaves this way? Real important thing to understand about statistics is what we're actually doing is we are boiling down the scenario to its most fundamental bits and pieces, just a small handful of numbers, and then from that we are extrapolating and making statements by a certain set of rules. Now, because we're ignoring those details at the outset, our answer in the end always has to fall within some sort of like error margin, a way to quantify how close your answer might be. But trying to wheedle away at these statistical arguments by making commentary on details is typically a waste of time. Like when we talk about pandemic modeling using those statistics, here's really all we're considering. If somebody has a disease, on average, how many people do they infect before they stop being infectious? Where are the sick people? What is the density of the population around those sick people? And really, that's it. There aren't any other considerations being made when we calculate out numbers about future projections, because to be honest with you, when it comes to dealing with very large numbers, small details, small changes made on the ground are irrelevant in the overall outcome. Nonetheless, basic vocab. Probability. Probability is the ratio that an event will happen per the total space of possible outcomes. Probability is simply a ratio that expresses a ratio, and this ratio contains the number of ways that a thing can happen divided by the total space of all possible outcomes. So if you can count up the numerator and the denominator of this ratio, you can determine the probability of any given outcome. This is to say that the probability of any given event E, where an event is just like a thing that could happen, right? This is going to be equal to the number of ways E can happen then divided by the number of ways anything can happen in the space of E. And so I think the best way to talk about this is to look at like some basic examples, right? And so for example, I roll 2 dice. What I want to know is, what is the probability the sum is, let's go with 4. Yeah, what's the probability the sum is 4? And then a second example to look at, I draw a card from a deck of cards. And I want to know what is the probability of spades, that I draw some card and it's just going to end up being of the suit spades. Yeah. So item number 1 out of these examples, right? I rolled 2 dice. What are the total possible outcomes? How many different ways can I get a result for rolling 2 dice?
12. Like there's 12 sides. Is that accounted for?
Not quite. In order to get the number of elements in the total space of rolling 2 dice, you have to employ a rule from 2 sections ago. One dice has 6 possible outcomes. The other dice also has 6 possible outcomes. How do I correctly combine those to get all possible outcomes, assuming those 2 events are independent? We drew a box to represent it. We did a little bit of math. I roll 2 dice, and then I take the sum. One dice has a grand total of 6 possible outcomes it could have. It could either roll onto side 1, 2, 3, 4, 5, 6. The other dice also has 6 sides. It could roll onto any outcome 1, 2, 3, 4, 5, 6. What are the total possible outcomes for 2 dice, each of 6 sides?
Is it not 12?
It is not 12, no.
36.
Is it a 3 out of 36
It is
possibility?
Yeah.
the
No.
denominator of this ratio. That is to say, the probability that we roll a sum of 4. The first thing that you want to figure out is typically that denominator, and that denominator is 6 times 6. Dice 1 has 6 outcomes, dice 2 has 6 outcomes. To figure out the grand total number of outcomes, we multiply. So that is to just add up the total number of outcomes for rolling 2 dice. Now what we want to do is we want to figure out, well, how many different ways could we roll up a sum of 4, right? So this is
2.
all possible outcomes in the space, right? And now in the numerator, I want to figure out how many ways I can get a sum of 4. So what are some dice pairings that give me a sum of 4?
2, 2,
I could roll pairs. I could get 2 and 2. What else could I get?
3, 1,
I could get 3 and 1. And what else? There's one more possibility.
1 and 3.
1 and 3. And so, since there are 3 different ways that I could roll 2 dice to get a grand total sum of 4, that is to say the probability of rolling a sum of 4 is exactly 3 out of 36, which simplifies down to 1/12, or sorry, 1/12. And so typically when y'all talk about probability, you usually end up discussing it in terms of what do most people talk about kind of as units of probability, though that's not normally correct.
Percent?
Yeah, usually people talk about various relative probabilities in terms of percent, just because it makes it like a nice chunk out of 100 to try and imagine. Though typically when you're talking about like scientific probabilities, we're very comfortable with things that aren't necessarily out of units of 100. But nonetheless, this is to say that a probability of 1/12 is a decimal. It's 0.08. But to turn it into a percent, you just take that probability and multiply it by 100, which is to say the chance of rolling 2 dice and getting a sum of 4, the chance of that happening is just over 8%. Is that okay?
Hey, Mr. Robinson, what's the difference between 1 and 3 and 3 and 1?
There are 2 dice. There's a difference between, if you had 2 dice that were color coded, a red dice and a blue dice, there is a difference between getting red on 3 and 1 on blue, or getting 1 on red and 3 on blue. But in either case, the sum is 4.
Okay, I see.
This is why, and I mean, I'll refer back to that diagram that we drew out when it came to rolling 2 dice, because like I said, this intro stuff is really odd to think about. But not all dice outcomes are equally likely when you are rolling 2 dice. It is overwhelmingly likely that you roll a sum of 7, because the chance of getting a 7 is actually 1/6 on its own for 2 dice. This grid has all possible sums, right? This one here, where up at the top edge, it's the first dice, on the left edge, it's the second dice. And you can see here that the diagonals on the inside all have the same sum. So of the 36 outcomes, only one of them can give you 2. You have to get snake eyes, right? Double ones. But when it comes to getting a sum of 7, you could do that by getting 1 and 6, or 2 and 5, or 3 and 4, or 4 and 3, or 5 and 2, or 6 and 1. So when it comes to rolling 2 dice, there are actually 6 different ways, 6 ways out of 36 that you could get a grand total sum of 7. Item number 2. From a deck of cards, what is the probability that we pull spades? So for saying how many cards are in a deck of cards?
52.
Yep, 52 individual cards in a regular deck of cards. And how many of them are spades?
13.
13 of them are spades. So this is to say that there is a 1/4 probability that you pull spades, or if you take this number and multiply it by 100, you would find that this is about this is precisely 25%. All of these representations are perfectly equal.
Mr. Robinson, are we working towards are these steps to work towards an answer, or are these answers? Would questions look like this?
No, because this is only the first topic. We haven't gotten to any of the interesting things yet that let you deal with more complicated problems. This is the correct. There aren't steps here the same way there are in algebra. Like, it's not like you have one tried and true method that always lets you work towards a correct answer. One of the biggest challenges about this section is knowing which method it is that you want to use upon reading a problem. Yeah, I can't say that there are discrete steps in statistics the same way there are in like doing regular old algebra or arithmetic. You read a scenario, choose an appropriate method for the scenario, and if the method is inappropriate, you get the wrong answer, and hopefully you have the tools to diagnose that, whether or not the answer you get is reasonable or unreasonable. Okay, so here are some rules that we have for doing combinations of events, which is far more interesting because in that previous question, right, where I talked about the deck of cards, that sucks. Like if you ran into me in an alley and I'm like, hey, draw a card from this deck of cards, and if it's spades, you win money, right? You're not going to play that game. That's just not an interesting game. Overwhelmingly, card games are about like combinations of cards in the form of hands, right? So if you play blackjack, we're not interested in the draw of one card. We're interested in the combination of two cards, or potentially what happens if you draw more cards past that. Same with poker. We're not interested in the drawing of one card. We're interested in the drawing of typically 5 cards and how they assemble into a hand. So after we have that basic definition of the probability of one event, we then become interested in defining how it is that we can take combinations of events. And so we have a couple different rules here. Rule number 1, the probability of a union. Which is the same as saying, what is the probability of getting E or F? And the magic word here is that this is how to combine probabilities using the word or. This is to say that when it comes to taking the probability of 2 events combined with the word or, we want to like tabulate this, add it up, by saying the probability of E in union with F, and it's the same union symbol from the domain and range stuff. It's basically just saying the combination of E and F is going to be equal to the probability of E and the probability of F. So we're just going to add them up. That is to say that when it comes to doing statistical stuff, the word or means addition. And then from this, we have to subtract the probability that E and F in somehow, like in some way, overlap with each other. And this part probably doesn't make too much intuitive sense, but let me go ahead and pin this down with an example. So for example, what is the probability, like let's say we're playing some game of cards, and we want to know what is the probability that you draw from a deck of cards, a 7, or a diamond. And so to use this rule that we have here for the probability of a union of events, that is to say that we want to find the probability that we draw a 7 or a diamond from a deck of cards. Well, that's going to be equal to the probability that we draw a 7 plus the probability that we draw a diamond minus the probability that we draw a 7 diamond. The reason why we have to subtract this is, I'll draw this out in a second so that it's very explicit, is the fact that if you were to simply just add them up, you would actually be double counting one of the cards. So let's go ahead and add this up real quick, right? So that is to say, what is the probability that you draw one card from a deck of 52 cards and get a 7? How many 7s are in a deck?
1 out of 13.
Let's not simplify.
No, okay, 4 out of 52.
4 out of 52. And then what's the probability that you draw a diamond?
13 out of 52.
Plus 13 out of 52. But then from this, you must then subtract the probability that you draw a 7 diamond. So how many 7 diamonds are there in a deck of cards?
1.
There's only 1. So minus 1 out of 52. And so we compute this little sum here. And so 4 plus 13 minus 1 gives us
16.
16 out of 52, which simplifies down to 4 and 13, or we could always turn that into a probability or a percentage or whatever. And so here's the deal with this, right? We only have a finite number of cards in a deck. We only have 52 cards in our deck. So in this list of 4 sevens, right, in that first one there, that is to say that this is contributing to our list of possibilities in our numerator, the 7 of diamonds, the 7 of clubs, the 7 of spades, and the 7 of hearts, right? This is the first 4 elements that we're counting up here. And what about this 13? What 13 objects is that counting up?
All the cards that are diamonds.
Yeah,
The
the entire suit of diamonds. So except me writing the list out this way. So that second thing is saying that to this first list of 4 objects, go ahead and add up all of the diamonds that are ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. All 13 of these cards in the list. But the problem is here, right, in trying to add up this event saying or, what is the probability that we draw a 7 or a diamond? What are we double counting? What's here twice?
The 7.
The 7 of
7
diamonds is included in both of these lists. Yeah, it took me a long time. I didn't understand this for years until somebody just like drew it out for me. Like, why are we subtracting? It's because this element is counted twice, the diamond 7. And so by subtracting it, we're not removing it in total. We're just removing one of them because it's a duplicate. So let's say we subtract one of the 52. So we subtract this one. And now this is a complete list of all of the cards that are 7s or diamonds with no repetition. The only point to this at all is this removes repeated elements. That's all that that object is doing. Is this question here, is that okay?
Yeah, now makes sense.
Okay. If we ask this question with an or, like this, yeah. If we ask this question or like this, right? And the probability of both of them occurring is 0, that is possible, then we refer to that scenario as being mutually exclusive. So if P of E and F is equal to 0, then E and F are recognized as being mutually exclusive, which is to say that there is no way that those two events can overlap. This is really just vocab that you'll see more of later in statistics. This is just the definition of what makes two things mutually exclusive, but you will find a whole bunch of conditions and riders and scenarios and additional rules and theorems that hinge on whether or not two things are mutually exclusive. So a quick example of two things which would be mutually exclusive. Roll 1 dice. Roll 1 die. And what is the probability that you roll 3 or 4? What's the chance that you roll 1 die and you get a 3 or a 4?
2 out of 6.
Yeah, so the chance that you get a 3, that's 1 out of 6. The chance that you get a 4 is also 1 out of 6. Each one of those have one of the 6 sides of the die assigned to them. And then from this, we must subtract, well, what is the chance that you roll a die and you get a 3 and a 4 at the same time? There's no such thing on a standard die. So this would be minus 0 out of 6. I only bring this up to say that 1, this has vocab associated with it. This is to say that on die, rolling 3 or 4, that's mutually exclusive, those two events. And also to tell you that sometimes you will attempt this method. Yeah, sometimes you will attempt this method and find that this is 0. That's fine. That happens. That is totally cool. You can absolutely use this approach and find that this is 0. That happens. Okay. I got 2 more rules, and then we'll look at some like spicier examples, I guess. Rule, well, what does that put us at? So the first one was a definition, and then I guess these other 2 are rules. So rule 3, the probability of a, God, what is the word? Oh, probability of simultaneous events. Which is to say, combining probabilities with the word and. What is the probability that things happen in conjunction with another, things happening at the same time, right? This is to say the probability of E and F, and this is typically equal to the probability of E multiplied then by the probability of F. So let's say that we are playing some board game that has a combination of pieces. Most good board games have like a weird combination of pieces that do the math for them on the board, like statistical objects, usually like a coin or dice, or if you're playing a good game like Dungeons and Dragons, hella different dice that have different number distributions on them so that the math is a little bit more interesting and too complicated to do quickly in your head, or spinners or whatever. So let's say that, for example, we are playing some game that has dice and cards and a coin. So what I want to know is, what is the probability that I flip the coin, roll the dice, draw a card, right? And we get the following outcome on our coin, dice, card turn. What is the probability that I flip the coin and I get heads? I roll the dice and I get 4 or greater. No, I'm sorry, 3 or greater. And I draw a card and it happens to be an odd number. That for some reason we're playing a game and this causes me to win on my turn. On my turn, I have a really good turn so long as I flip a coin, get heads, roll a dice, get 3 or greater, and then I draw a card and it's an odd number. If this occurs, I win. So what is the probability that I win on my next turn? So first off, right, we're going to say that all 3 of these events are independent. There's nothing magic that connects the coin to the dice or the dice to the cards or the cards to the coin. So I can process each one of these individually. This is to say that if I want the probability of heads and 3 or greater, which I could represent this way, and an odd number is just going to be equal to the probability that I get heads multiplied by the probability that I get 3 or greater multiplied by the probability that I get an odd number out of that deck. So let's go ahead and take each one of these individually. What is the probability that I flip a coin and get heads?
Half.
It better be, otherwise it's a fake coin, right? It's a trick coin. What is the probability on a dice that I get 3 or greater?
4 out of 6.
I got 3. I got 4. I got 5, and I got 6.
Yep.
So that's 4 out of 6. And then what's the chance that I reach into a deck of cards and I pull out an odd number?
$26.
So let's consider how many cards are in a deck of cards. Well, that's going to be 52. And then what are the number cards in a deck of cards?
Like how many there are?
Yeah, in a deck of cards, how many odd numbers are there?
Oh,
Four.
Sorry,
Right.
which four?
16. 6.
Well, there's 4 individual numbers: 3, 5, 7, 9.
Right.
3,
And then
5, 7, 9. And then of the 3, 5, 7, 9, how many suits are there of each of those cards?
Oh, 4.
4
So
times
yes.
4 is
16.
excellent. And so this product right here, multiply across the top, multiply across the bottom, will tell us what the probability is that you win flat out on the next turn. So that is to say 64 in 624. Or we could take these two and simplify them, which this is going to give us 4 over 39. Or again, you could always turn that into a percentage by multiplying by 100. So this right here is about 10.26%. You have about a 10% chance of winning if this is your requirement of winning on your next turn. Is this okay for this third rule? Is this okay?
Yeah, it looks good.
Okay. And so that leads us to our final rule, which is something that we've already been using before. The last thing that we need to talk about is what is the probability of a complement. So the probability of a complement which is to say E naught. So typically the probability of an event E is E, and then the probability of its complement is E prime. This is basically to say, what is the event that E doesn't happen? So not E, the opposite of E. Whatever event E is, I want E prime, with that little apostrophe on it, to be the exact opposite. Well, the trick here is that notion that we talked about last section called normalization. That is to say that if I have a set of events, and this set of events is exhaustive, right? Like I add up all of the probabilities, well, for the world to make sense, they have to add up to 1. The chance that an event will occur needs to necessarily be 100%. This is to say that if I consider all of the outcomes on a one die, there are 6 of them. I could roll 1, 2, 3, 4, 5, or 6. The chance that I get a 1 is 1 in 6. The chance that I get a 2 is also 1 in 6. The chance I get a 3 is 1 in 6. The chance I get a 4 is 1 in 6. The chance I get a 5 is 1 in 6. The chance I get a 6 is also 1 in 6. If you take 1 over 6 and you add it back to itself 6 times, you get 6 over 6, which simplifies to 1. That fact must be true for effectively all probabilistic scenarios, that all of the events have to add up to 1. And so from this, I can make the following, I guess, manipulations. The probability that E occurs combined with the probability that E does not occur, that better add up to 1. What's the chance I roll a 1 on a set of die? Well, that's 1. What's the chance that I don't roll a 1? Well, that's 5 in 6. No matter what, the chance that an event occurs and the chance that an event doesn't occur needs to add up to 1. So if we know this, we can always get that. This is to say that the probability that event E does not occur should always be equal to 1 minus the probability that the event E does occur. This is a very useful trick because sometimes there might be a lot of things here. It might be hard to figure out what the probability is that an event doesn't occur. So if you can figure out the probability that it does occur, it's always easier to subtract in order to reverse engineer this value. Let's give an example. Would somebody like to explain for us the simple rules of blackjack? How does blackjack work?
You need to get to 21.
So we are trying to
with the
sum our
sum of
cards to
cards.
21. We want to sum our cards to 21. And what happens if the sum goes over 21?
You go bankrupt. You
Yeah.
you lose the hand.
You bust, right?
Yes.
And so here is the scenario that we are currently living under. Imagine we're sitting at a table playing a game of blackjack. The dealer has 2 cards, and one of the cards that the dealer has is secret, and one of the cards that the dealer has is exposed. And then here are your cards, right? So this one is secret, the other one is exposed. Let's go ahead and say that the dealer is exposing a 10 of diamonds, okay? And then your hand is secret to you. The dealer can't see it, but you know what's in it. And here is what is in your hand. Let's say that you have a 10 and a 7. You have the 10 of hearts and the 7 of diamonds. So here's what I want to know. What is the chance you do not bust? Which is the same as saying, and whenever I ask a question of this nature, I always make sure to like ask it mathematically and not within the lingo of the game. What is the chance that you draw another card and you do not go over a sum of 21?
So the highest card we could get is a 4, and then everything down.
So what is the chance that you do not bust?
Because
So, huh?
Because you're at 17, so you're either gonna go to 21 or you're gonna stop at 20 or 19 or.
Right. So here's what I'm actually getting at, right? There are 2 ways that we could figure this out. If you want to figure out what is the chance that you draw some additional card and you don't bust, right? The chance that you do not bust is going to be equal to 1 minus the probability that you do bust. So the probability that you do not bust is equal to 1 minus the probability that you bust, because this is exhaustive, right? Any given card is either going to keep us below 21 or push us over. So I can say that the chance that we don't bust is equal to 1 minus the chance that we do bust. And in this scenario, I think this is easier to figure out, the chance that we go over 21. So right now our sum is at 17. So when it comes to that next card, right? What would happen if we drew a 5?
We bust.
Yeah, because that would take us to 22. So as long as we score 4 or under, we do not bust. But anything higher than that will cause us to bust. And we can show that. Yes?
Do we count ace as ones for this question?
Aces count as, well, yeah.
1s or 11.
They can count as 1 or as 11, but since we're at 17, any ace we acquire would be counted as a 1. So here's what I want to show. I want to show that both calculations of this, both calculating it directly and calculating it as 1 minus, will give us the exact same thing. So if we draw a 4 or lower, we're good, right? We don't bust. Right? So we can calculate the probability that we don't bust directly. So this is to say all of the ways that we can get 4 or lower go in the numerator, right? And how many cards are in the deck?
52.
I'm going to disagree with you there. How many cards are in the deck?
Oh, 48.
Yeah, notice there's already 4 cards dealt out here, and that's a common feature of any question that involves a deck of cards. Since 4 of the cards have been dealt out of the deck, they have been removed from the deck, and they are no longer in the denominator. So the probability that we bust is going to be equal to the number of cards remaining in the deck that are 4 or lower, divided by the 48 cards left in the deck. However, here's a problem that makes this a little bit more, you know what, that's fine, we'll leave it there. So 4 or lower divided by 48. And how many cards in the deck are 4 or lower?
16.
It could be ace.
Or no, way more, I think.
4 or lower, it's ace, 2, 3, 4, and then there's 4 suits. So yeah,
16,
16. So this is going to be equal to 16 divided by 48. So that's one answer. That is sufficient. We could also get the probability that we do bust. which is to say the probability that we get what card causes us to bust?
5 or higher.
5 or higher. Then divided by 48. Because again, 48 cards remain in the deck. And so how many cards remain of 5 or higher? Five or higher?
32.
We have 5, 6, 7, 8, 9, 10, Jack, King. So that's 8 cards. And then how many suits?
4 of them, so there'd be 32.
So this is going to be equal to 32 out of 48. And that shows that the sum of these two things here, right? The sum of those two adds up to 1. So we could either approach it directly and get the probability that we don't bust and say that this is equal to 16 over 48. Or we could take this as a complement, which is to say 1 minus the probability that we do bust, where the chance that we bust here is 32 out of 48. Is this okay?
Yep.
Now there is a complication here. There is a slight wrinkle that messes up our application of this. And what is that? Go ahead and move this up just so you know.
The card's already shown.
Yeah, one of the cards is already known. We know one of the dealer's cards. So what does that affect about our analysis here?
But Ms. Johnson, didn't we account for that when we removed it from the denominator?
We did, but we would actually need to also remove it from the numerator.
But only in the case of the second fraction, right? Because you're counting everything above 5.
We are counting everything above 5, but we're saying that everything above 5 that we're unaware of is already accounted for in that deck.
Yeah, but the dealer might have anything higher as well, so you don't have to subtract 1.
This isn't problematic, it's this.
Yeah, you don't know what he has.
You don't know what this has, but notice that we effectively ignore it down here in our counting, right? We're saying that like we're not really concerned with what that card is. And when it comes to statistics, even though it feels unnatural to not do any math that somehow includes that unknown, right? That is the correct and proper thing to do from a statistical perspective. You leave unknown information alone, and we don't attempt to treat it in this. Because if, like, depending on what this card is, it might remove a potential card from this set or that set. But so long as we don't know what card that is, we're just going to act like it's still in the deck. We're going to act like it doesn't interfere with our outcomes. True, you subtract it from the denominator because it's already gone, but having information about that additional card would actually affect the way that we do the math here. Yeah, it's a weird one. Okay, so let us talk now about some wrinkles of this. Where is it that this stuff gets truly difficult? And I actually just lost my last sheet of white paper. Let me grab a fresh pack. Yo, I bought like a fat brick of Target printer paper before we went home to do like from home learning. I just chewed up the whole thing. I got to finish on graph paper. Sorry about that. Let's look at some fancier examples. So let's say that we're playing a game of poker. And when it comes to poker, right, let's say that we're doing 5-card poker. No substitutions. Typically, when you play a game of poker, depending on exactly what rules you're using, you can substitute cards in and out, which is to say if you have a hand of 5 cards and you don't like 2 of them, you can return 2 of them to the dealer in exchange for 2 more. That could make your hand better. It could also make your hand worse. It just depends on how you're playing. It's also a way of signaling what is in your hand to other players. If you toss 2 cards, it means that you probably had a bad hand to begin with. Blah, 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 blah. That removal of 2 cards and then addition of 2 cards back to your hand makes analyzing poker fairly complicated, statistically speaking. you can do it. We can do it. We'll probably look at that tomorrow. But for right now, let's go ahead and imagine that for this example, this is the most straightforward version of this that we could have, right? That is to say, you just get dealt 5 cards. That's it. So let me ask you, what is the probability of a royal flush? Which, if you don't know, the royal flush is the most powerful hand in poker. A royal flush causes you to instantly win. There's nothing that can beat it in the world of poker. When you play poker, you're basically comparing one hand to another, and whichever hand has a higher value, that person wins the money if it gets to that point, right? If the other people don't fold. Does anybody know out there, what is a royal flush?
Is it 10, Jack, King, Queen, Ace?
10, Jack, King, Queen, Ace, and all of what's the additional rule on top of this? Normally this is just a straight.
They have to be in the same suit.
Same suit.
They have to be in the same suit. How about that? And so if I want to find the probability of a royal flush, this is going to be equal to the number of ways that this can happen. How many ways can that happen? How many different ways can you get 10, Jack, King,
4.
Queen, Ace?
4
Why is it
times.
4?
4 suits.
There's 4 suits.
Because there are 4 suits. That is to say, we're not worrying about how we get these cards individually or whatever, right? What we're actually interested in is how many independent ways can this happen? Well, in any given deck of cards, there are 4 independent royal flushes, and either a heart royal flush, spade royal flush, heart royal flush, diamond royal flush. Now, the hard part, what is the denominator of this probability? That is to say, how many different hands can be dealt out in a game of poker? Assuming you have no knowledge of any other active cards, you have no idea what is in anybody else's hands. In order to figure out this denominator, we need to go ahead and we need to fall back to a further section from the past, and we need to ask ourselves the crucial question, does the order matter when it comes to being dealt a hand of cards in poker? If I handed you Jack, 10, Queen, King, Ace, is that still a royal flush?
Yeah.
It is. So you're telling me the order doesn't matter.
Right.
Nope.
Big hint. What is our denominator here? If the order doesn't matter, is that a permutation or a combination?
Oh, it's some computation.
Sorry, permutation or combination?
Combination.
If the order doesn't matter, then this is actually a combination, which is to say, of the 52 cards in a deck of cards, a poker hand takes and combines 5 of them. And so if you want to know what the probability of pulling a royal flush is, well, that's going to be 4, then divided by all possible poker hands, which is 52 C 5, which is a pretty big number. There are a lot of possible unique poker hands. In one deck of cards, there's about 2.5 million different poker hands. And so our probability is 4 divided by this, which if you want to turn into a percent is still radically small. This still simplifies down to 0.12315%. Lots of people go their entire lives playing poker regularly and never hit on a royal flush. The chance is about, it's comparable to 1 in a million. And actually, if you take into account the actual wrinkles of poker, like other people being dealt cards, your knowledge of other cards, these odds are slightly lower than this. It's about 4 in 4 million. Is this okay? Is this all right?
Yeah. Yeah, that
Okay.
looks good.
Yep.
So when we come in tomorrow, today I'm going to post the last homework. And then when we come in tomorrow, we'll have time to work on that assignment and get our questions answered there. I'll also put some spicier questions than this into the warm-up, some harder ones, like what's the chance of getting a full house or whatever, right? we'll look at some more complicated constructions of these probabilities. And just like super full disclosure, just so that you know, this homework that I'm about to put up is the last homework assignment of the school year, obviously, considering the school year ends in a few days. There will be a warm-up that I collect from this week at the end of the week. But you should know that I drop lowest homework. So if you have all of the homework up to this point, you don't really need to do this homework or turn it in. Like, of course, do it for your own benefit, but just so you know, I drop lowest homework. So if you're all the way done up to now, doing this homework assignment will not affect your grade. I'll put it up now. You can take a look at it, and I will see you all tomorrow. And we'll have a warm-up with some harder probability questions. We'll work on the homework, and then we'll head off to summer. Is that okay?
Yeah, sounds good.
Cool. You all have a very
Sounds
nice
good.
day, and I will see you all tomorrow.
See you tomorrow.
Yep.
Thank you, Mr. Robinson.
Bye. Have a nice
Thanks.
day.